This system isn't fixed. It only looks that way. Clouds are not constant shields. Their brightness can shift. When it does, the world adjusts. Weather patterns shift. Harvests move. Electricity demand reshapes. Not over centuries, but within seasons. A measurable nudge, then momentum. The first changes are subtle, the later ones are not. By the end, the world still functions differently. One shift triggers another. If clouds reflected more sunlight naturally, Earth would keep less of the sun's energy. Skies brighten in a Milky Way. Light softens. Midday heat eases. You notice it on skin before in data. Less absorbed, more reflected. Farmers, engineers, and city planners would see the shift in yields, loads, and light. Not sudden, persistent. A chain reaction, not a single event. From the ground, clouds act like an ever-changing roof over our world. But this roof isn't solid. It's a dynamic collection of countless suspended water droplets and ice crystals, all riding currents of rising air. Each one is a tiny mirror. When sunlight strikes a cloud, some of that light reflects directly back into space. The rest scatters, filtering through as the diffuse, gentle warmth we feel on an overcast day. This reflectivity is called albedo. A cloud's albedo isn't fixed. It depends on the size and number of its droplets, its overall thickness, and its altitude. Think of it like a shattered mirror. A single large piece reflects light in one direction. But break it into 1,000 tiny shards, and it scatters light everywhere, appearing far brighter. The same is true for clouds. For a given amount of water, more smaller droplets create a brighter, more reflective cloud. Cloud type and altitude also play a crucial role. Thick, low clouds like stratocumulus are excellent coolers, acting like a sunshade for the Earth's surface. But thin, high cirrus clouds, made of ice crystals, are less reflective. They tend to trap heat radiating up from the planet, creating a warming effect. So by day, clouds are shields. By night, they become blankets. The planet's temperature is a delicate balance of both functions. If clouds over the ocean were to become just slightly brighter, their daytime cooling effect would strengthen. The fundamental process remains the same, it's just amplified. The global energy balance would tip, slightly but significantly, toward cooling. This doesn't require creating a new type of cloud. It simply means encouraging the formation of finer, more numerous droplets within existing marine clouds. On the ground, the change would be subtle. The harsh glare of direct sun would ease. Light would feel more like it does in a photography studio, soft and even. Shadows would lose their sharp edges and begin to blur. If you were to look up, you'd notice more days with a milky white haze near the sun and a less intensely deep blue sky at midday. Sunrises and sunsets would linger, their colors stretched into richer, more complex gradients by the enhanced scattering of light. These physical changes trigger others. Cooler ocean surfaces would gently nudge the paths of storms and alter regional wind patterns. Rainfall patterns would shift in response. Forest growth would adjust to the new light and water conditions. Animals, in turn, would follow these changes. Our own systems, power grids, agricultural schedules, architectural designs, all built for yesterday's light and weather, would need to recalculate and adapt. It begins with physics, but meteorology, biology, and eventually society all follow in a quiet but persistent cascade of effects. The change itself is designed to be measurable, not dramatic. A nudge, not a shock. Understanding the sequence of these impacts is critical. What feels the change first? The atmosphere's heat balance. What shifts next? Rain and routine. The order matters. On the ground, the changes feel subtle at first. Afternoons ease, especially in the sweltering tropics and during continental summers. The intense, baking heat of midday begins to soften. Harsh, direct sunbeams yield to a brighter, more diffuse ambient light. It's a world seen through a natural softbox, where shadows lose their hard edges. Daily life recalibrates. Plans, clothing, and even moods adjust to this gentler heat, making outdoor activity more pleasant during peak hours. This cooling has a direct impact on weather. Less intense surface heating means less convective fuel for the powerful afternoon thunderstorms that define many climates. In storm-reliant regions like Southeast Asia, the once predictable monsoon showers can thin or shift their timing, disrupting ancient agricultural cycles. As natural rainfall becomes less reliable, irrigation demand rises, and municipal water budgets feel the strain. But the atmosphere is a connected system. Altered winds can steer storms along new paths, pushing moisture into once dry zones. Gentle, soaking rains may trade places with intense, localized downpours. The map of flood and drought risk is effectively redrawn. The global water cycle seeks a new, sometimes volatile, equilibrium. Drought here, deluge there. The oceans, holding immense thermal inertia, answer these changes on a much slower timescale. Not in years, but over decades to centuries. A cooler ocean surface acts like a brake on glacial melt. It doesn't reverse the process, but it can slow the rate of ice loss at the margins of Greenland and Antarctica. Over many decades, this could mean the rate of sea level rise slows, granting vulnerable coastal communities precious more time to adapt. Even a slight nudge to surface temperatures can alter polar sinking and deep ocean flows, causing the planet's heat transport patterns to edge into new routes. Regional climates feel this oceanic shift slowly, almost imperceptibly. The timeline for these adjustments spans generations. The changes are powerful, but they are not loud. In the water, life responds. Phytoplankton, the base of the marine food web, track the shifting patterns of light and temperature. Entire productivity zones migrate, and where the plankton go, everything else follows. From the smallest krill to the largest whales, the timeless rule holds. Food follows food. This migration forces fishing fleets to chase their stocks into new waters. For coastal economies, it means some ports boom, while others wait for fish that may never return. For fragile ecosystems like coral reefs, even a slight and temporary cooling of the surface can ease the stress of bleaching cycles, an uneven, localized but very real reprieve. For our energy systems, the changes are a complex trade-off. On one hand, fewer brutal heat waves mean less strain on aging power grids during peak summer demand. The risk of rolling brownouts on the hottest days decreases, and utilities burn less expensive, often carbon-intensive fuel from peaker plants that only run when demand is highest. But there's a direct downside for solar power. While panels still generate electricity from diffuse light, their output is significantly lower than under direct, unimpeded sun. In regions like Germany or the Pacific Northwest, where solar capacity has grown, projections for peak generation may consistently underperform, complicating the energy mix. This forces utilities to lean more heavily on other dispatchable sources like natural gas or hydropower to fill the gaps. The economic models underpinning renewable investments are recalculated, factoring in a new baseline for solar unreliability. It's not just solar. Shifting atmospheric circulation remaps historic wind regimes, making some turbine farms more productive while stranding others. Hydropower follows the new patterns of rain and snowmelt, altering reservoir levels and power potential. To manage this increased variability, grid-scale batteries and stronger inter-regional connections become not just helpful, but essential infrastructure to buffer these weather-dependent gaps. At the household level, the story is similar. Home solar yields dip, but that loss is often balanced by lower air conditioning costs. In our cities, lower daytime heat directly reduces public health emergencies like heat stroke, especially among the vulnerable. The quality of urban life can tangibly rise. However, the brighter, more uniform ambient glare from the cloud cover pushes architects toward new types of anti-glare glass and dynamic shading strategies. Inside, the need for more artificial lighting during the day creates a slight uptick in energy use, offsetting some of the savings from reduced air conditioning. City planners must update their strategies, adapting cooling centers, parks, and tree cover plans for a gentler but fundamentally different urban heat profile. For agriculture, the consequences are profound. Sun-loving staple crops like corn, sugarcane, and tomatoes can see their growth slow under softer light. Yields may dip even with milder temperatures, as they receive less of the direct solar energy needed for photosynthesis. As rainfall patterns are redrawn, some farming regions face new irrigation burdens, while others contend with waterlogged fields and a rising threat from fungal diseases that thrive in damp, overcast conditions. Fundamentally, what grows where begins to change. Global supply chains shuffle to adapt, and food prices respond to the new realities of production. But farmers are masters of adaptation. They pivot, developing new crop cultivars bred for lower light, adjusting planting and harvest calendars, and using precision technology to apply inputs with centimeter-level accuracy. This isn't a story of collapse, but one of immense, system-wide reorganization. The new winners and losers will be defined by how quickly and effectively they can adapt. The physics of a brighter, cooler world sets the stage. The choices we make will play out the scene. A cooler tendency in many places, but rainfall shifts redraw risk. Ocean warming slows, ice loss breaks, timelines lengthen. Grids relieve peaks, but replace missing solar. Budgets and markets rebalance. Heat stress declines in some cities. Flood and drought migrate to new addresses. Reflective clouds mask symptoms. They do not cut greenhouse gases. Treat it as slack to accelerate transition, or a pretext to stall. Observe, learn, adapt. Continuously. Systems keep rebalancing. Choices keep steering. What scenario should we explore next? Share your ideas below. You've been watching IfVerse, where imagination meets possibility. See you in our next reality.